This is the ELEC 1510 Logic Design Lecture 5 Video 2 on Karnaugh Maps, corresponding to textbook section 3.2. Karnaugh maps are used to graphically simplify functions because, as you probably know by now, simplifying functions algebraically is confusing and difficult, and you never quite know when you're done simplifying the function. Sometimes a very large function can be simplified all the way down to one variable, and it's hard to ever know when that's true unless you're really good at it. And the Karnaugh map, or K-map way, is a very simple graphical way to do all of this simplification. So let's look first at simplifying a simple function algebraically. This simple function is f equals xy plus xy prime. If we factor out an x from this expression, we have x and y or y prime, and we know that y or y prime is 1, so this function simplifies just to x. Okay, so you can do all of this simplification algebraically. What we want to do, though, is once we get into much more complicated functions, is do everything graphically. So one of the things to realize is that these two minterms, assuming that f is only a function of x and y, these would be minterms, have only one variable that is changed states between them. So only y has changed states. For example, x, y is the minterm 3 for 1, 1. X, y prime is minterm 2 for 1, 0. So the 1 is the same in these minterms, and the 1 and the 0 have changed in the second place. So there are 4 possible minterms: 0, 0 for minterm 0, 0, 1 for minterm 1, 1, 0 for minterm 2, and 1, 1 for minterm 3. So if we look at these, 0, 0 and 0, 1 have only one bit that's different, the second one. So the 0 stays the same. If we look at 0, 1 and 1, 0, both of the bits have changed. So those are not combinable because, or immediately combinable because both bits have changed. 1, 0 and 1, 1 have one bit that changes between them. The second one, the first one is a 1 the whole time, so it doesn't change. Basically what this means is any two minterms that only have one variable that changes state between them can always be combined. So if I have something like a, b, c, d, or a, b, c, d prime, these are the minterms 1, 1, 1, 1 and 1, 1, 1, 0. Now all of the bits have stayed the same except for the last one. So these can be combined. Any two minterms that have more than one bit that changes state can't be immediately combined. And there's a way to represent all of this graphically. So if I plot in a table as a function of the variables, say x can be either a 0 or a 1, so I'll write that the horizontal axis here is x, and y can be either a 0 or a 1 in terms of the minterms. Now, if x is a 0 here and y is a 0, then that's minterm 0. If x is a 0 and y is a 1, that's minterm 1. If x is a 1 and y is a 0, that's minterm 2. And if they're both 1, that's minterm 3. Any two minterms that are next to each other in this chart can be combined. So, for example, minterm 0 and minterm 2, I can circle those and they can be combined. Minterm 2 and minterm 3 I can circle and they can be combined. 1 and 3 can be combined. 0 and 1 can be combined. Now, what gets a little complicated is that this chart isn't big enough to make this worthwhile, but any minterms that are on opposite sides can also be combined. Now, we don't have enough variables for this to be significant at this point, but that'll become more significant with more variables. Now, obviously, minterm 0 and minterm 3 are not immediately next to each other, and so they can't be combined. Similarly, minterm 2 and minterm 1 are not right next to each other, so those can't be combined either. Okay, so we know that xy is 1, 1, corresponding to minterm 3, and xy prime is 1, 0, corresponding to minterm 2. So now what I'm going to do is, in this chart, I'll put a 1 in the chart whenever the minterm is represented in the equation. So minterm 0 wasn't in the equation, so I'll put a 0 there. Minterm 1 wasn't in the equation, but then 1 and 3 were in the equation. Now what I want to do is circle adjacent minterms in the chart, and then I can combine them into a single term. And now how I combine them is by looking at what that bubble covers. If the bubble covers a variable and it covers both states of that variable, then that variable is not included in the term that the bubble represents. So for example, here x is only ever 1 in that bubble. The bubble doesn't cover where x is 0, but it covers y being both 0 and 1 because it's vertical across y equals 0 and 1. So y is not a part of that expression, but x is, and x is not complemented because it's a 1. So that bubble is just x. And as we know, we simplified this function algebraically and it came out to be x, and so the bubble represents the simplified expression, x. Okay, so two variable k-maps you're not going to see very often because those are very easy to simplify algebraically. A three variable k-map is going to be much more common. Let's just say that the three variables that we use here are x, y, and z. So this could be a function of x, y, and z represented in this k-map. So now all of the 8 possible minterms can be represented in this k-map. Where x and y are both 0 and z is 0, that's minterm 0. Where x and y are 0 but z is 1, that's minterm 1. Then we have minterm 2 and minterm 3. Okay, now the tricky part about k-maps is that if we were to write the binary numbers counting up sequentially, 1, 0 counting, 0, 1 counting up to 1, 0 is not sequential. Both of the bits have changed state, moving from 0, 1 to 1, 0. So we actually write 0, 1 to 1, 1 because then the 1 stays the same, but the 0 changes to a 1 here. And then 1, 1 changes to 0, 1. So then minterm 4 is here, minterm 5 is here, then minterm 6 and minterm 7. So keeping track of that sort of irregular distribution of the minterms in the k-map is very important. Okay, so let's simplify a function then using a three variable k-map. We have a function of x, y, and z is the sum of minterms 3, 4, 5, 6, and 7. So I'm going to fill in the variables here. It doesn't necessarily have to be x, y on the horizontal and z on the vertical. You can change it, but that's probably going to be the most simple in this case. So minterms 3, 4, 5, 6, and 7 are all part of this expression. So I'm going to put a 1 in the k-map wherever those minterms are. So minterm 3 is right here, minterm 4 is here, 5, 6, and 7. Now the rest of the minterms are not in the expression or the function, so I'm going to put zeros there. And now what I want to do is circle bubbles of 1s. And I want to make the bubbles as big as possible. So the first bubble that I see that's pretty big is all of these 1s are adjacent to each other. All right, now I need to figure out what the expression for that bubble is. And what I do is I look for terms in that bubble that don't change. So let's first look at z. The bubble covers both possible values of z here, 0 and 1, so z is not represented in that expression. If I look at y, well, y is the second variable here, and it's 1, 1, and 1, 0, so y was 1, and then y was 0. Y changes states in that bubble, so it's not represented. That means that x is the only variable that doesn't change state, 1 to 1, so this bubble is just x. Okay, I still have one hanging one here that needs an expression covering it. So let's circle an adjacent 1. Now I can't circle an odd number of 1s, it has to be an even number of 1s. So please keep that in mind. I couldn't have extended this out to the right farther. That doesn't work. It has to be an even number of 1s. So now the expression for that bubble is, well, let's see. X was 0 and X was 1, so X changes state. So X is not part of that expression. Y was 1 and 1, so we have a Y. And Z was 1, so YZ. So the total expression for this function then is just the sum of those bubbles, X or YZ. And again, you can have overlapping bubbles. That's totally fine. Sometimes overlapping bubbles can be redundant, and so that wouldn't lead to an optimized expression, but as long as they're not redundant, you can have overlapping bubbles. All right, so let's do a little more complicated of a function now. Minterms 0, 1, 4, and 5. So minterm, in terms of x, y, and z, so let me fill in my variables. Minterm 0 is right here, so there's a 1. Minterm 1 is right here. Then we have 2, 3 are zeros, 4 and 5 are 1s, and 6 and 7 are zeros. Now what you might be tempted to do, simplifying this expression, is to circle these bubbles. And that would give you, let's see, x prime y prime plus x y prime for those bubbles. But that's not an optimized expression, actually. Because K-maps wrap around, and so you can actually circle a bubble that wraps around the outside edges of the K-map. You have to be careful about that. Sometimes they're hard to spot. And so in this bubble, z is covered by the bubble, so z is not a part of that expression. Y is a 0 and a 0, so we're going to have y prime. And then x is 0 and 1, so x is not a part of that expression. So y prime is the expression for this function. All right, now let's simplify a function when you're not given a sum of minterms, you're just given an algebraic function here. This means that you have to work backwards and figure out what the bubbles are from the expression. So now we have a, b, and c instead of x, y, and z, so I'll fill in the variables there. A, b, c prime is when a is 0, b is 0, and c is 1. So I have to look for a being 0, b being 0, and c being 1. So I'll fill in a 1 right here. bc, now this is not a minterm, bc, that's a simplified sum of minterms, but bc is where b is 1 and c is 1. And because we don't have an a, we would assume that a is both 0 and 1. So we have to look for where b is 1, so that's here and here. And now a was both 0 and 1, so the bubble will actually cover both of these values. And then c was 1, so that's here. So now we have 2 1s right there. And the last expression, a, b prime, c, is where a is 1, b is 0, and c is 1. So a is 1 here, b is 0, and c is 1, so we have a 1 here. Now it should be fairly obvious how you simplify this function by drawing a bubble. The bubble is down at the bottom row. And so that bubble has all possible values of a and b. A was 0 and 1, and b was 1 and 0. So a and b are not a part of this expression for this bubble. The only thing that is c. That was the only part that wasn't changing. C was 1 for that whole bubble, so that bubble is c. And c is the simplified expression. So if you were to algebraically go through and simplify this function, you would get to c. All right, so that's all of the examples I'm going to do for K-maps here, and I'll do quite a bit more in class.